400 million years ago, the air itself was a poison to creatures like us. This is the story of how life fought back, not with teeth or claws, but with wood and roots. By the end, you will understand the hidden force that built the breathable, temperate world we call home. We will uncover how silent forests cooled an entire planet and why their success led to oceanic catastrophe. What ancient choice do you think still shapes our sky today? To set the stage for the forest revolution, we must first step back into the world before it. Forget the green landscapes you know. The land was a canvas of rock and ruddy soil, baked under a thick, soupy atmosphere. Carbon dioxide levels soared to over 10 times what we breathe today, trapping heat in a powerful greenhouse effect. The global average temperature was several degrees warmer, a true hothouse planet where the poles held no permanent ice. Life huddled at the water's edge. The continents, fused into the vast southern supercontinent called Gondwana, were dominated by silent, empty expanses. In the wet lowlands and along the margins of shallow seas, the only vegetation was a thin, green fuzz. Primitive mosses and liverworts clung to damp ground, and the earliest vascular plants, simple stems without true leaves or roots, crept slowly inland. They were pioneers, but they were not yet engineers. In this world, the carbon cycle was stuck in a kind of climatic gridlock. Volcanoes steadily pumped carbon dioxide into the air, but there was almost no natural mechanism to pull it back down and lock it away. The planet was quite literally holding its breath, a pressure cooker with no release valve. The stage was set for a transformation, and the key would not be a fearsome predator or a dramatic catastrophe, but a quiet, structural innovation deep within the plants themselves. The true catalyst for change was not a grand event, but a microscopic innovation. Deep within the cellular structure of these pioneering plants, evolution engineered a new molecule called lignin. Think of it as nature's first version of reinforced concrete. This complex polymer, tough and rigid, was woven into the walls of plant cells, giving them a structural integrity never before seen on land. With this internal scaffolding, plants could now defy gravity. They could grow upward, competing fiercely for the most precious resource in that dim, crowded world, sunlight. The race for the canopy had begun, but lignin came with a profound, unintended consequence. For the decomposers of that era, the bacteria and fungi whose job it was to break down dead plant matter and return its carbon to the atmosphere, lignin was an impenetrable fortress. Their biological toolkits contained no enzymes capable of digesting this stubborn new material. When a lignin-fortified plant died, it did not rot away quickly. Instead, it persisted. This created a critical bottleneck in the planet's carbon cycle. For millions of years, carbon had flowed in a relatively quick loop, from air to plant and back again. Now, with lignin, it began to stall. Carbon was being pulled from the atmosphere through photosynthesis, and then, instead of being released, it was being locked away in growing piles of undecomposed wood and plant debris. The world was about to experience its first great carbon sink, built not by geology, but by biology's own success. This biological bottleneck was the quiet prelude to a planetary transformation. Into this waiting world stepped Archaeopteris, a life form so revolutionary it is often called the first true tree. Picture not a towering oak or a dense pine forest, but a sprawling, sunlit grove of plants with woody trunks, deep-reaching roots, and a canopy of fern-like leaves. Archaeopteris was the architect of Earth's earliest forests, and its arrival changed everything. These were not the shadowy, closed canopy woods we know today. They were open, park-like environments where light filtered through to the ground, creating a mosaic of brand-new habitats, but the real revolution was happening out of sight. The extensive root systems of Archaeopteris did something unprecedented. They physically and chemically attacked the bedrock. For the first time in Earth's history, plant roots were digging deep, fracturing rock and secreting acids to mine nutrients. This process, called weathering, unlocked minerals from the stone, but it also triggered a critical chemical reaction. As the roots broke down silicate rocks, those minerals reacted with carbon dioxide dissolved in rainwater, forming solid carbonate compounds that washed away to the sea. This was a direct mechanical method of pulling carbon from the air and locking it into the geologic record. Above ground, the trees performed their own silent work. Each falling frond and piece of bark, each trunk that eventually toppled, added to a growing layer of litter on the forest floor. And remember, this material was fortified with that indigestible lignin. So it piled up, a slowly thickening blanket of carbon-rich organic matter that simply would not rot. Forest by forest, grove by grove, Archaeopteris was not just decorating the landscape, it was building a massive, biological carbon capture machine. The planet's thermostat was being turned down, not by a volcano or an asteroid, but by the relentless, quiet growth of the world's first trees. This hidden machinery of roots turned the ground itself into a planetary cooling system. To understand how, picture a simple raindrop falling through that ancient, carbon-rich sky. As it descends, it absorbs carbon dioxide, becoming a weak carbonic acid, a natural soda water. Before forests, this mildly acidic rain would simply splash against bare rock, beginning a slow, almost imperceptible process of erosion. But with the arrival of deep root systems, everything changed. The roots acted like a network of billions of microscopic drills and chemical factories. They physically pried apart bedrock, creating vast new surface areas for that acidic rainwater to attack. More critically, the roots themselves secreted organic acids far more potent than the rain, actively dissolving the minerals within the stone. This supercharged breakdown of rock is what scientists call enhanced silicate weathering. Here is the brilliant climatic alchemy. The key minerals in granite and basalt, silicates, contain elements like calcium and magnesium. When the root acids break these minerals down, they release these elements. They then combine with the carbon dioxide from the rainwater, forming new, stable compounds like calcium carbonate. These compounds dissolve, are washed away by streams and rivers, and finally settle in the ocean depths. There, over eons, they become part of the sedimentary rock record, a literal tomb for atmospheric carbon. So with every inch a root grew, it was not just seeking water and nutrients, it was performing a slow, relentless subtraction. It was pulling a minute, invisible amount of carbon dioxide from the air and converting it into stone at the bottom of the sea. Multiply this process across the spreading forests of an entire supercontinent, and you have a planetary-scale thermostat being cranked down, degree by imperceptible degree, across millions of years. The lush green world above was merely the visible sign of the silent, radical work happening in the dark below. But the story of carbon capture did not end with roots and weathering. Above the ground, another process was unfolding, one that would leave a permanent mark on our planet's geology and our own industrial history. The forests themselves were becoming a kind of living tomb for atmospheric carbon. Remember, the lignin that gave trees their strength was a substance that the decomposers of that era simply could not digest. When a tree fell in those ancient forests, it did not vanish back into the soil within a few seasons. Instead, it joined a growing, tangled mat of undecayed wood, bark, and leaves. In the warm, wet lowlands and swampy basins of the supercontinent, this material piled up into immense, waterlogged layers of peat. This was not a quick process, but a slow, relentless accumulation over millions of years. Layer upon layer of organic matter was buried by sediment washed in from rivers, sealed away from the oxygen that might have allowed some decay to occur. Under the immense weight of overlying rock and the planet's own internal heat, this peat underwent a slow alchemical transformation. The water was squeezed out, the complex organic molecules broke down and recombined, and over vast stretches of deep time, that spongy plant matter was compressed and cooked into something new, something black and dense and packed with ancient sunlight coal. This grand burial is what scientists call long-term carbon sequestration. The carbon that those trees had pulled from the air to build their trunks and leaves was not being returned to the atmosphere in any meaningful time frame. It was being permanently removed from the active cycle of life, air, and ocean, and locked away into a deep geological vault. The forests of the Devonian and the following Carboniferous period, named for its incredible coal deposits, effectively built the planet's first massive carbon capture and storage system. They were not just cooling the world in the moment, they were banking that coolness, creating a climatic savings account by burying carbon on a scale almost impossible to comprehend. The coal that powered the Industrial Revolution, the very substance that reshaped human civilization, was the fossilized legacy of this ancient atmospheric cleanup project. It is a profound irony that we later mined and burned these deposits, releasing carbon that had been safely sequestered for over 300 million years back into the air in a geological instant. But for the ancient planet, this great burial was the final, decisive step in a climatic revolution, pulling the world from a stifling greenhouse toward a new, cooler equilibrium. What happens, though, when a planet's thermostat is turned down too far? The planet's great cooling had reached a tipping point. For millions of years, the silent work of roots and the relentless burial of wood had been pulling carbon dioxide from the air, slowly turning down the global thermostat. But climate systems possess a powerful inertia, and the full effect of this biological engineering was not felt immediately. It arrived as a delayed reaction, a climatic echo of those ancient forest success. As carbon dioxide levels continued their long, slow plummet, the atmosphere's ability to trap heat diminished. Earth's natural greenhouse blanket grew thinner. The warmth that had defined the Devonian world began to seep away into the void of space. Global average temperatures started to fall, degree by degree, over millions of years. This was not a sudden freeze, but a profound and gradual chilling that reshaped the entire planet. The lush, humid landscapes that had nurtured the first expansive forests began to change. In the high southern latitudes of the great supercontinent Gondwana, where landmass covered the polar region, the cooling had its most dramatic effect. Winter snows began to persist through the summer. Year after year, the snowpack deepened, compressing under its own weight into glacial ice. These ice sheets grew, slowly at first, then with gathering momentum, spreading outward from the poles in vast, grinding rivers of ice. This marked the beginning of the late Paleozoic Ice Age, one of the most severe glacial periods in our planet's history. The world the first forests had built, a world of warmth and abundant carbon dioxide that allowed them to thrive, was now vanishing, replaced by a colder, drier, and far more climatically volatile globe. The very life forms that had triggered this revolution now had to contend with its consequences, a planet entering a deep freeze of their own making. The cooling climate did not operate in a vacuum. It set in motion a series of powerful, self-reinforcing cycles that accelerated the planet's descent into an ice age. This is the principle of a positive feedback loop, where an initial change triggers effects that amplify the original trend. The growing ice sheets were the most visible engine of this acceleration. Their brilliant white surfaces acted like a planetary mirror, reflecting a far greater portion of the sun's energy back into space than the dark rock or green forests they covered. This measure of reflectivity is called albedo. As ice spread, Earth's albedo increased, meaning less solar heat was absorbed by the surface. This caused local temperatures to drop further, which allowed the ice sheets to expand even more, which then reflected even more sunlight. It was a runaway cooling cycle, a climatic snowball effect in the most literal sense. Meanwhile, the oceans played their own critical role. Cooler water has a greater capacity to absorb gases, including carbon dioxide. As the global temperature fell, the world's oceans became hungrier, drawing down even more of the remaining atmospheric carbon dioxide and dissolving it into the depths. This further thinned the planet's greenhouse blanket, which led to more cooling, which in turn allowed the oceans to absorb yet more gas. Each process fed the other, locking the planet into a deepening chill. Even the forests themselves, the original architects of this change, may have contributed to the feedback loop in subtle ways. The vast, leafy canopies released immense amounts of water vapor through a process called evapotranspiration. This increased local humidity and potentially seeded more cloud cover. Clouds, depending on their type and altitude, can also reflect sunlight, adding another minor but persistent nudge toward a cooler state. What began as a biological innovation, the simple act of a tree growing wood and roots, had cascaded through the entire Earth system. It moved the global climate past a critical threshold, a tipping point from which it could not easily return. The stable, hothouse world of the early Devonian was gone, replaced by a new, icy equilibrium that would dominate for millions of years. The forests had succeeded so completely that they had rewritten the rules of their own existence. Yet for all the transformations on land, the true price of this revolution was being paid in the sea. The same relentless weathering that pulled carbon from the air had an unintended and devastating side effect. As roots broke apart the continents, they unlocked a torrent of nutrients, minerals like phosphorus and iron that had been locked in rock for eons. Rain and rivers carried this rich soup into the shallow coastal seas, delivering a sudden, overwhelming feast to the simplest forms of marine life, the algae. What happened next was a phenomenon we now recognize all too well, but on a planetary scale. The oceans experienced catastrophic algal blooms, vast green clouds of microscopic life exploding across the sunlit surface waters. For a short while, this might have seemed like a burst of oceanic fertility, but the bloom contained the seeds of its own destruction. When those countless algae cells completed their brief lives, they died and sank into the darker waters below. There, armies of bacteria went to work, decomposing this raining deluge of organic matter. Their work required oxygen, and they consumed it at a staggering rate, stripping it from the surrounding water. This process, known as eutrophication, began to suffocate the sea from the bottom up. Vast stretches of the ocean floor, and then the water column above it, became oxygen-depleted zones or anoxic dead zones. In these waters, nothing that needed to breathe could survive. The gentle balance of the marine world was shattered. This widespread oceanic anoxia, this deadly lack of breathable water, became a primary driver of the late Devonian extinction, one of the 5 most severe mass extinction events in our planet's history. The victims were almost entirely marine. Elaborate reef systems built by coral-like organisms called stromatoporoids collapsed entirely. Whole families of armored fish, trilobites, and ancient ammonoids vanished. The vibrant, complex ecosystems that had dominated the seas for millions of years were choked and starved of oxygen, not by a sudden impact from space, but by a slow, fertile poison washing off the continents. It is a profound and sobering paradox. The very biological machinery that cooled the global climate and created new opportunities for life on land, the roots and forests, simultaneously unleashed a cascade of events that devastated life in the oceans. This is the starkest possible reminder of Earth's deep interconnectedness. A change in one sphere, the geosphere, through weathering, triggered a change in the biosphere with algal growth, which altered the chemistry of the hydrosphere, leading to a catastrophic loss of biodiversity. The planet's systems do not operate in isolation. They are a single, intertwined engine, and a revolution in one realm can echo as a catastrophe in another. This atmospheric transformation created a new kind of world, one with a different chemical signature, as the relentless burial of carbon-rich plant matter removed vast volumes of carbon dioxide from the air. It did something profound to the remaining atmosphere's composition. The relative proportion of another gas, oxygen, began to climb. This oxygen was the primary waste product of the same photosynthetic process that built the forests, a stream of breathable air released as trees turned sunlight and carbon dioxide into wood. With the carbon dioxide being locked away and not replaced, this oxygen accumulated, perhaps reaching concentrations significantly higher than the 21% we enjoy today. The air itself was being remade, becoming thinner, drier, and far more energetic. This was the final, crucial gift of the ancient forests. They forged the very air that would enable a new chapter of life. An oxygen-rich atmosphere is not just about breathability, it is about power. It allows for more efficient respiration, meaning cells can generate more energy from the same amount of fuel. This new high-octane air opened an evolutionary door that had been firmly shut. It permitted the development of larger, more active, and more complex bodies that required greater metabolic fuel. On land, this energy surplus paved the way for the first true terrestrial vertebrates. Lobe-finned fish, already equipped with robust fins, could now venture further from the water's edge, their descendants evolving into the earliest amphibians that crawled through the humid undergrowth of the expanding coal swamps. But the most striking testament to this supercharged air may be found not in the vertebrates, but in the invertebrates. In the following Carboniferous period, the high oxygen levels allowed insects to achieve sizes that seem fantastical to us today. Dragonflies with wingspans the width of a hawk, millipedes as long as a human leg. These giants were possible because the dense oxygen could diffuse more effectively through their simple respiratory systems, supporting massive bodies that would collapse under their own weight in our modern atmosphere. So while the forests cooled the planet and triggered oceanic hardship, they also performed a quiet miracle of alchemy. They transformed a stifling, carbon dioxide-rich sky into a vibrant, oxygen-rich one. The air we now depend upon, the air that fuels every runner, every bird in flight, every thought in our own brains, was in large part a legacy crafted by those silent, woody pioneers. They built not just a climate, but the fundamental chemical precondition for a world of movement, activity, and ultimately, consciousness. This grand narrative of forests and climate is not a theory spun from thin air. It is a story painstakingly deciphered from the pages of the earth itself. The proof is locked in stone, in coal, and in the very chemistry of ancient materials, waiting for scientists to learn its language. At sites like the Gilboa Fossil Forest in New York, paleobotanists uncover ghostly remains of the world's first trees. They find massive, fossilized stumps still anchored in the ancient soil, their sprawling root systems perfectly preserved in the rock. These are not just impressions of leaves, but the actual structural remains of entire ecosystems frozen in time, offering a direct snapshot of that park-like Devonian woodland. Meanwhile, geochemists work with a different kind of clue, one written at the atomic level. They analyze the ratios of different isotopes, or atomic variants, of carbon and oxygen found in ancient limestone layers and in the carbon atoms within the fossilized plant matter itself. These ratios act as a chemical fingerprint, recording the dramatic plunge in atmospheric carbon dioxide and the corresponding rise in oxygen. It is as if the ancient air left a signature in every shell and every piece of buried wood. The sedimentary record provides the final, undeniable chapter. In the same geological strata, we find two seemingly contradictory deposits layered one atop the other. First, vast beds of coal, the compressed remains of those immense, undecayed forests, and directly associated with them in the geological timeline, we find clear evidence of glacial activity, like distinctive scratch marks on bedrock and deposits of unsorted rubble called tillites carried by long-vanished ice sheets. This is the concrete evidence, the smoking gun. The coal proves the forests existed and were buried on a colossal scale. The glacial deposits prove the world turned cold. Their coexistence in the rock record is the definitive link, showing cause and effect separated by millions of years but preserved together in Earth's archive. This multidisciplinary detective work, combining botany, chemistry, and geology, transforms fragments of the deep past into a single, coherent narrative. It confirms that the quiet growth of roots and wood did not just change the scenery, it changed the entire planet, and the rocks have been waiting to tell us all along. That ancient story of forests and climate is not just a fossilized curiosity, it is a direct, if inverted, parallel to the world we inhabit today. The Devonian Revolution was a planetary-scale experiment in carbon management, and we are now running the same experiment in reverse. For millions of years, those first forests and their successors performed a slow, natural form of carbon capture and storage, pulling carbon dioxide from the air and locking it away in coal seams and carbonate rock. Humanity, in a geological instant, has become the agent of rapid carbon release, mining and burning those very coal deposits to power our civilizations. The mechanism is opposite, but the underlying lesson from the rocks is the same. Profound changes to the planet's carbon cycle trigger profound and often unpredictable changes to the entire Earth system. The geological record does not whisper this lesson, it shouts it. We see the evidence in the glacial deposits that followed the Great Carbon Burial and in the oceanic layers that mark a mass extinction. It demonstrates with brutal clarity that when you alter the fundamental chemistry of the atmosphere and oceans, you alter everything. The ancient event teaches us about the power of feedback loops, those self-reinforcing cycles that can accelerate change far beyond the initial push. In the Devonian, cooling led to ice, which reflected more sunlight and caused more cooling. Today, warming melts reflective ice and snow, revealing darker land and ocean that absorb more heat, leading to more warming. It is the same physical principle, just flowing in the opposite climatic direction. This deep time perspective also lays bare the fragility of interconnected ecosystems. The Devonian forests, thriving on land, inadvertently starved the oceans of oxygen. Our own actions on land, from agriculture to industry, now create similar dead zones in coastal waters through nutrient runoff, a haunting echo of that ancient stress. Perhaps the most sobering lesson is one of legacy. The choices made by those primitive plants, the evolutionary innovation of lignin, reshaped the planet for over 100 million years. The climatic consequences of our current release of buried carbon will likewise echo for millennia, not just centuries. Understanding this ancient event is not about assigning blame, but about gaining crucial insight. It provides a long-term dataset, a real-world test of how Earth systems respond to major carbon cycle disruptions. This knowledge is vital for refining the computer models that project our future climate, grounding them in the reality of our planet's deep past. It forces us to appreciate the staggering scale and inertia of natural systems, and the lasting footprint we are creating in real time. The story of the first forests is ultimately a story of unintended planetary engineering, a reminder that life itself is a powerful geological force. We have now inherited that force, and the ancient rocks offer us a clear warning and a profound responsibility to understand the system we are changing before the change becomes the next chapter written in stone. This delay presents one of the most intriguing puzzles in the entire story. If lignin and deep roots were such powerful climate tools, why did the planet's deep freeze wait for tens of millions of years? The timeline itself holds a clue. The first woody plants, the pioneering architects, appeared in the Middle Devonian period. Yet the most dramatic plunge in carbon dioxide and the onset of major glaciation unfolded much later across the late Devonian and into the Carboniferous period. This gap suggests the climate system possesses a profound inertia, and that biological innovation alone was not enough. It needed to reach a critical mass, a planetary tipping point. Researchers are piecing together several compelling explanations for this long lag. One central idea is sheer coverage. A few scattered groves of Archaeopteris, no matter how effective their roots, could not reshape a global atmosphere. The real cooling likely began only when these forests achieved continental-scale dominance, forming interconnected networks that covered vast stretches of the supercontinent Gondwana. This expansion would have taken immense time, as plants slowly adapted to drier inland areas and new ecological niches opened. Another factor may be the evolution of the root systems themselves. The earliest woody plants had relatively shallow roots. Over generations, natural selection favored individuals that could dig deeper to access water and nutrients locked in the bedrock. This evolutionary arms race, pushing roots ever downward, would have gradually but exponentially increased their weathering power. The deepest roots contact more rock, secrete more acids, and ultimately pull far more carbon from the air than their shallow ancestors. So the climate tool itself was being refined and amplified over millions of years. Geology may have provided the final amplifier. During this same era, massive mountain-building events like the rise of the Appalachian Mountains were crumpling the edges of continents. These new, towering ranges exposed immense fresh surfaces of silicate rock to the atmosphere. When the ever-expanding forests sent their root networks into these newly uplifted, unweathered slopes, it was like turning the weathering machine to its highest setting. The biological signal of the roots was suddenly supercharged by a geological event, creating a perfect storm for carbon drawdown. This lag, then, is not a flaw in the story but a testament to its complexity. It reminds us that Earth does not change with the flip of a switch. It responds to the slow, cumulative pressure of life, geology, and time all working in concert until finally the balance tips. But the story of lignin did not end with a permanent planetary lockbox. For millions of years, the carbon stored in wood seemed invulnerable, a dead end in the cycle of life. Yet nature abhors a monopoly, and evolution is the ultimate problem solver. The logjam in decomposition was finally broken by a quiet, unassuming kingdom of life, the fungi. In the dark, damp spaces of the forest floor, a new kind of organism evolved a biochemical key. White rot fungi developed a unique enzymatic toolkit, most notably a powerful molecule called lignin peroxidase. This enzyme acted like a master skeleton key, capable of dismantling the complex, interlocked bonds of the lignin fortress that had baffled all other decomposers. For the first time in over 50 million years, the vast energy bank stored in fallen trees was no longer off-limits. This was a revolution in recycling. The fungi did not just break down the wood, they unlocked it, transforming a permanent tomb of carbon into a flowing stream of nutrients. The ancient piles of undecayed plant matter, which had been slowly accumulating into coal, could now be processed and returned to the soil. Carbon that had been on a one-way trip to geological storage was now redirected back into the active web of life. This evolutionary arms race between plants building stronger defenses and decomposers crafting better tools introduced a critical feedback loop into the global system. It prevented all of the planet's carbon from being permanently buried, which would have eventually starved future plant life of the carbon dioxide needed for photosynthesis. The rise of these fungi marked a profound new chapter in ecosystem dynamics. A fallen tree was no longer just a monument to the past. It became a bustling city for microbial life, a nutrient-rich nursery for new growth. It illustrates a fundamental truth of our living planet, that life continually adapts to reshape its own environment. No innovation, no matter how successful, remains unchallenged forever. The balance of the carbon cycle, so dramatically tilted by the first forests, was slowly, patiently restored by the silent work of threads in the dark, proving that in the long story of Earth, every lock eventually meets its key. The legacy of those first forests stretches far beyond the chemistry of the air. While they were busy rewriting the planet's carbon budget, they were also performing a quieter, equally profound act of engineering, this time with water. The greening of the continents launched a revolution in the very way Earth manages moisture, transforming chaotic floods into life-giving rivers and turning dry winds into nourishing rain. This was the birth of the modern water cycle as we know it. Before forests, rainfall on barren land was a story of sudden loss. Water would hit the hard-packed ground and immediately race downhill as destructive runoff, carving deep gullies and stripping away precious topsoil in violent flash floods. It was a landscape of extremes, either parched or flooded, with little in between. The introduction of deep, woody root systems changed this equation completely. These roots acted like a vast, living sponge network. They physically held the soil together, creating a stable, porous structure that could absorb and retain rainwater. Instead of rushing away, water now seeped down, replenishing underground aquifers and being stored in the soil itself. This simple act of retention had cascading effects, slowing the destructive power of erosion and giving the land a newfound resilience against drought. The soil beneath our feet, that complex, life-filled layer that supports all terrestrial ecosystems, was in many ways a creation of the forest. But the trees did not just store water, they also became active participants in moving it. Through their leaves, they released water vapor into the air in a continuous process called transpiration. A single, large tree can release hundreds of liters of water into the atmosphere each day. Now envision an entire continent of trees performing this act, a silent, colossal geyser of moisture rising into the sky. This massive injection of water vapor fundamentally altered local and regional weather. It increased humidity, seeded cloud formation, and quite likely created a feedback loop where forests literally generated their own rainfall. Rain would fall, be absorbed by roots, travel up the tree, and be exhaled back into the air to fall again as rain further inland. This biotic pump effect allowed forests to spread their own climate, turning arid interiors into habitable, humid environments. This transformation reshaped the very arteries of the continents, the rivers. In a barren landscape, rivers are flashy and unreliable, raging torrents after a storm and dwindling to a trickle in dry periods. A forested landscape creates rivers of remarkable consistency. The sponge-like soil regulates the flow, releasing stored water slowly and steadily into streams throughout the year. This created stable, perennial waterways with defined banks and fertile floodplains, the perfect cradles for new forms of aquatic and amphibious life. The forest, therefore, was not just a passive feature on the land. It was an active, living system that manufactured its own stability. It built the soil, managed the water, and even summoned the rain, crafting a diverse array of new freshwater habitats, from shaded forest streams to broad, meandering rivers. In doing so, it unlocked a whole new suite of possibilities for evolution, inviting life out of the seas and into a world now rich with sheltered, watered, and interconnected homes. Yet even this compelling story is not a closed book. Within the halls of paleoclimatology, a vibrant debate continues, a healthy sign of a science still actively questioning its own conclusions. While the broad strokes of the forest revolution are widely accepted, the precise details, the exact mechanisms, and their timing remain a fascinating puzzle. Some researchers look at the same evidence and propose a different weight for the forces at play. They suggest that perhaps tectonic activity, the slow dance of continents, played an even larger role than the roots themselves. A period of reduced volcanic activity, for instance, would have naturally lowered the amount of new carbon dioxide being pumped into the air, allowing any drawdown from weathering to have a much more dramatic effect. It is a debate about primary drivers, asking whether biology was the lead actor or a powerful supporting player in the climatic drama. Other scientists scrutinize the geological timeline, questioning just how synchronized the cooling was across the entire planet. The data from one continent does not always perfectly match the sequence from another. Was this a single, smooth global transition, or a more staggered series of regional climate shifts that eventually merged into a new ice age? This debate pushes for ever more precise methods of dating ancient rocks and correlating events across the globe, and the tragic story of the Devonian extinctions in the oceans is itself a subject of discussion. While the nutrient runoff from the new forests is a prime suspect, some studies suggest other marine processes, like changes in ocean circulation or the upwelling of toxic deep waters, may have contributed significantly. These are not disagreements that undermine the story, they are its essential refinement. Each controversy forces scientists to gather better data, build more sophisticated models, and look at the problem from new angles. This is how scientific understanding deepens, not by accepting a single neat narrative, but by relentlessly testing it against every piece of contradictory evidence. The unresolved questions remind us that the deep past is a complex tapestry, and we are still learning to read every thread. To unravel this ancient climatic mystery, scientists employ a kind of digital time machine. They use general circulation models, or GCMS, which are the same powerful computer simulations that forecast our modern weather and future climate scenarios. But instead of today's satellite maps, they feed these models with a reconstructed ancient world. This includes paleogeographic maps of the supercontinents, estimates of the sun's slightly younger output, and critically, the reconstructed atmospheric soup of gases like carbon dioxide and oxygen. The challenge, of course, is knowing what numbers to put into the model. This is where the field of paleoclimatology becomes a masterclass in detective work. Researchers turn to natural archives, physical records locked within the Earth itself. They analyze ancient soils called paleosols, which preserve chemical signatures of the atmosphere that formed them. The ratio of certain carbon isotopes in these soils can act like a fossilized breathalyzer, revealing the concentration of carbon dioxide in the ancient air. Another ingenious proxy comes from the plants themselves. Scientists study the density of tiny pores called stomata on the surfaces of fossilized leaves. These microscopic openings through which plants breathe in carbon dioxide and exhale oxygen become more numerous when carbon dioxide levels are low, as the plant needs to work harder to gather the gas. It is a beautiful example of life recording its own environment. By combining these disparate data points, from soil chemistry to fossilized leaf anatomy, researchers can build a surprisingly detailed profile of the Devonian atmosphere. They then plug these numbers into the general circulation model and hit run. The supercomputer essentially rewinds the planet, simulating millions of years of weather patterns, ocean currents, and heat distribution. This allows for virtual experiments. What happens if we remove the forests from the simulation? Does the ice still form? What if we lower the mountain ranges or change the ocean's chemistry? By tweaking these variables, scientists can test which factors were truly essential in pushing the planet over the climatic edge. It is a process of elimination played out across silicon processors, helping to distinguish between mere correlation and true causation in the deep past. These models do not give us a perfect video replay of ancient Earth, but they provide our best possible understanding of the forces and feedbacks that transformed a greenhouse world into an icehouse, offering invaluable context for the changes we observe in our own time. The black veins of coal we extract from the Earth hold more than just energy. They contain a story 300 million years in the making. Each lump is a time capsule of that ancient atmospheric cleanup project, a physical piece of the Devonian and Carboniferous worlds. When we ignite it in a power plant or a furnace, we are not merely burning rock, we are unlocking a geological vault. In a flash of heat and light, we are returning carbon atoms to the air that were pulled down by the first forests, atom by atom, over countless generations. The timescales involved are almost impossible to reconcile. Those trees performed their work across tens of millions of years, a slow, patient subtraction that gradually cooled the planet. Our industrial era is compressing that entire, epic process of release into a mere few centuries. We are reversing their climatic engineering not just in direction, but at a speed thousands of times faster. This creates a profound and sobering historical loop. The very biological innovation that created a stable, oxygen-rich climate capable of supporting large, active life forms like us now provides the substance that threatens to destabilize that very system. The coal that powered the steam engine, lit the cities, and built the modern world is the fossilized sunlight of a revolution that once saved the planet from a runaway greenhouse. We are, in a very literal sense, burning the remains of our own climatic benefactors. This deep time perspective frames our current challenge not as an isolated event, but as the latest chapter in a very old story. It reminds us that the carbon cycle is not an abstract concept, but a tangible thread connecting the deepest past to our most urgent present, a thread woven from wood, root, and now smoke. The planet's new climate was not a barren icebox but a cradle of unprecedented opportunity. With the establishment of stable forests, rivers, and a breathable atmosphere, the stage was set for life to explode in directions never before possible. The cooling and drying of the globe did not create a biological desert. Instead, it forged a world of distinct, stable habitats, from the humid, lowland coal swamps to the cooler, drier uplands. This diversification of real estate was the single greatest catalyst for the evolution of terrestrial life. For the first time, there were countless new niches to fill, each with its own unique challenges and resources, and evolution rushed in to fill every single one. The first to truly capitalize on this new world were the arthropods. In the thick, oxygen-rich air and amidst the endless buffet of decaying plant litter on the forest floor, creatures like millipedes and the earliest insects underwent a spectacular radiation. Freed from the constraints of low oxygen, some lineages grew to staggering sizes, their segmented bodies supported by the dense atmosphere, becoming the first large consumers and recyclers in these new ecosystems. They turned the fallen world of the forest into a thriving, bustling metropolis of tiny legs and clicking mandibles, but the arthropods were just the opening act. A far more profound transition was occurring at the water's edge. Lobe-finned fish, already equipped with robust, fleshy fins supported by bones, began to venture into the shallow, weed-choked margins of streams and swamps. These were not yet land animals, but they were perfectly pre-adapted to navigate a world of tangled roots and temporary pools. Over generations, natural selection favored those who could push a little further, hold their breath a little longer, and use their fin bones to shuffle across a muddy bank to the next pond. From these hesitant explorations emerged the first tetrapods, animals with 4 true limbs. They were clumsy, crocodile-like creatures, but they were pioneers. They found a land of plenty, rich with arthropod prey and devoid of any large predators. The forest floor litter, that spongy layer of undecayed material, was not just a carbon sink, it was a shelter and a hunting ground. The stable river systems created by the forests provided nurseries and highways, and that supercharged, oxygen-rich air fueled their metabolisms, allowing for more sustained activity out of the water. This was the true legacy of the climate revolution. It built the house and then filled it with life. The physical changes to the planet triggered an unstoppable evolutionary cascade, an arms race of adaptation and innovation that, from those first crawling tetrapods, would eventually lead to every bird, every lizard, and every mammal that walks the Earth today. This grand experiment in planetary management raises a profound question. Is Earth's remarkable climate stability a lucky accident or something more? To find the answer, we need only look to our closest neighbors in the solar system and their starkly different fates. Venus is a cautionary tale of a greenhouse effect gone unchecked. Its thick atmosphere, almost entirely carbon dioxide, traps solar heat with such ferocity that surface temperatures soar high enough to melt lead. Any water it once possessed boiled away eons ago, leaving a scorching, bone-dry world. Mars tells the opposite but equally bleak story. Its thin atmosphere, also rich in carbon dioxide, cannot hold onto the sun's warmth. What water exists is permanently frozen in polar caps and subsurface ice, making the surface a cold, radiation-blasted desert. Both planets represent climatic extremes, and crucially, both appear to be worlds where geology and physics alone dictate the conditions, with no moderating influence from a living biosphere. They are, in a sense, climate control systems stuck in one position, with no ability to self-correct. Earth, by stunning contrast, has danced between these two extremes for eons, avoiding the permanent furnace of Venus and the deep freezer of Mars. The story of the first forests provides a powerful clue as to why. Our planet possesses something they lack, a biological thermostat. Life itself, through processes like weathering, burial, and even the evolution of new decomposers, has repeatedly nudged the global climate back from the brink, maintaining conditions within a band that allows life to not just survive, but to thrive and diversify. This idea that living things actively participate in regulating their planetary environment is sometimes called the Gaia hypothesis. It suggests Earth operates not as a passive rock, but as a complex, self-regulating system where life and its physical surroundings are inextricably linked. The Devonian forests are a prime example of this in action. They did not simply adapt to their world, they remodeled it. They cooled the air, enriched the soil, and crafted the rivers, all while creating the oxygen-rich atmosphere that would fuel future evolutionary leaps. This perspective reframes our understanding of life's role. We are not mere passengers on a geological ride, subject to the whims of rock and gas. For billions of years, biology has been a co-pilot, an active participant in steering the planetary system. It means the long-term habitability of our world is not a preordained gift, but a dynamic, ongoing achievement, a delicate balance maintained by the countless interactions between everything that lives and the ground, water, and air it inhabits. The silence of Venus and the stillness of Mars speak volumes about what makes our blue marble so rare and so precious. From a cosmic perspective, Earth began to put on its most recognizable feature. The transformation from a world of mineral tones to a living canvas would have been visible across astronomical distances. The ruddy browns and stark grays of exposed rock, occasionally tinted by reddish algal mats in damp areas, slowly gave way to a new color, the vibrant green of chlorophyll. At first, it would have been mere specks and smudges along coastlines and river valleys, like a painter testing a new pigment. But as the decades turned to millennia, those specks merged into patches. The patches expanded into vast, unbroken swaths, until entire continental regions wore a cloak of living green. This was not just a change in scenery, it was a fundamental shift in the planet's very identity, from a geological orb to a biological one. The color green, a wavelength of light reflected by the photosynthetic machinery within every leaf, became the universal signature of life on our world. It announced to the universe that this was not just another rock, but a place where sunlight was being harvested, where chemistry was being directed by coded instructions, where an entirely new kind of order had taken root. This greening was the most profound aesthetic shift in our planet's history, turning a monochrome landscape into a tapestry of texture and pattern. from the fractal branching of tree canopies to the dappled light of the forest floor. The pale blue dot was no longer just blue, it was now unmistakably, verdantly alive. This profound shift in our planet's identity carries a deeper philosophical weight. It challenges a very old way of seeing the world, one that neatly separates the living from the non-living. For centuries, we have viewed geology as the slow, patient work of rock and lava, of continents drifting and mountains rising, a grand but lifeless stage. Biology, in this view, was merely the play performed upon it, a temporary and fragile spectacle. The story of the first forest shatters that division. Here, life was not a passive occupant of the geological stage. It was the stagehand, the set designer, and the director all at once. The Russian scientist Vladimir Vernadsky gave us a powerful term for this reality, the biosphere. He did not see life as simply existing within Earth's layers, but as an active, transformative geological force in its own right. The Devonian forests are the perfect testament to this idea. Think about it, a biological innovation, the evolution of lignin and roots, directly controlled the rate at which continents weathered. It determined what kind of sediments rivers carried to the sea. It rewrote the chemical formula of the global atmosphere, and in doing so, it set the planetary thermostat for 100 million years. Where does the rock end and the root begin? When a tree's acidic secretion dissolves a piece of granite, is that a biological act or a geological one? The answer is both, inseparably. This forces us to see Earth's history not as two parallel tracks, one for life and one for the planet, but as a single, braided narrative. The air we breathe, the soil underfoot, the very climate that defines our existence, are all products of this endless conversation between the living and the once living. Our world is not a planet that just happens to have life on it. It is a planet that has been fundamentally shaped and continues to be shaped by the life it holds. This perspective transforms our understanding of home, revealing a world where every breath is part of an ancient planetary dialogue that began with the first silent forests reaching for the sun. So can we borrow a page from this ancient playbook? The profound lesson of the Devonian is not just a history lesson, it is a potential blueprint. In the face of our current climate challenge, scientists and policymakers are actively exploring what are called natural climate solutions, strategies that harness the power of living systems to manage atmospheric carbon, inspired directly by that deep time past. The most visible of these is the global push for afforestation, planting trees where there were none, and reforestation, restoring lost woodlands. On the surface, this seems like a direct mimicry of the Devonian process, using trees as biological pumps to draw down carbon dioxide. And it works. A growing forest is indeed a carbon sink. But the ancient story holds a crucial caveat about scale and time. The first forests cooled the planet over tens of millions of years, not decades. Our emissions are occurring at a pace thousands of times faster than their drawdown. This means that while planting trees is a vital and valuable piece of the puzzle, it cannot, by itself, offset the sheer volume of carbon we are releasing from those ancient coal vaults. The forest is a slow, patient technology, and we are facing a rapid, urgent crisis. This realization has spurred more innovative approaches. Some researchers are looking beyond the trees to the power of roots and rock. They are experimenting with enhanced weathering, a modern attempt to supercharge that ancient chemical reaction. The idea is to take abundant silicate rocks like basalt, grind them into a fine powder, and spread them over agricultural fields. As rainwater and soil microbes interact with this powder, it accelerates the natural process that locks carbon into carbonate minerals. It is an attempt to turn entire landscapes into active carbon capture sites, leveraging agriculture itself as a climate tool. Yet even here, the deep time record whispers a note of caution. The Devonian revolution worked because it was a sustained, planetary scale phenomenon that became woven into the fabric of Earth systems. Our interventions, however well-intentioned, are local and temporary by comparison. They are additions to a system, not a transformation of the system itself. So the ultimate lesson from the first forests is not a simple prescription to plant more trees. It is a masterclass in systems thinking. It teaches us that to manage a planet, we must first understand its deepest rhythms, the million-year cycles of carbon, rock, and life. This knowledge does not offer a quick fix, but it provides something more valuable, a long-term compass. It informs where natural solutions can be most effective, how they might be scaled responsibly, and what unintended consequences, like nutrient runoff, we must vigilantly avoid. It grounds our modern strategies in the reality of Earth's own operating manual, reminding us that true sustainability means working with the grain of planetary time, not against it. The deep green of the forest is woven into the very fabric of human imagination. Long before we understood their role in crafting our atmosphere, forests held a sacred place in the human heart. Across cultures and continents, they appear not merely as collections of trees, but as realms of profound mystery and power. The Druids of ancient Europe held their rituals in sacred groves, believing these spaces were conduits to the divine. In the folklore of Japan, forests are home to kami, spirits that demand respect and reverence. And who can forget the enchanted woods of fairy tales, those dark, whispering places where heroes are tested, witches dwell, and transformations occur. These are not random settings. They point to a deep, almost primal understanding that the forest is a world apart, a place where the normal rules of the human domain do not fully apply. It is a space of both danger and sanctuary, of fear and awe. This universal archetype suggests something profound. While no human eye saw the first Devonian groves, our species evolved in a world already shaped by their legacy. For millions of years, our primate ancestors lived in the dappled light of woodlands, relying on the forest for food, shelter, and protection. That evolutionary history is etched into our subconscious. The feeling of peace under a canopy, the slight unease when the path disappears into shadow, the sense of being in the presence of something ancient and alive, these may be echoes of a deep time memory. They are an ancestral recognition, written in myth and instinct, that forests are not just a resource to be used. They are the fundamental architects of the breathable, temperate, water-rich world that made our very existence possible. Our stories of magical woods and sacred trees are, in a way, a cultural psyche paying homage to its oldest and most essential benefactor. This layer of meaning completes the narrative, connecting the cold, hard data of carbon isotopes and fossil roots to the warm, living pulse of human wonder. It reminds us that the story of the first forests is not just a chapter in a geology textbook. It is the foundational prologue to every legend, every campfire tale, and every quiet moment of reverence we have ever felt standing beneath the ancient, silent giants. The profound legacy of the Devonian forests now frames a pressing question about our own time. If the rise of woody plants marked the moment life became a conscious geological force, then what do we call the era where a single species wields that same power with intention? Many Earth scientists argue we have already crossed that threshold, entering a proposed new chapter in our planet's history called the Anthropocene, the age of humans. Just as the first trees rewrote the rules of air and rock, human industry, agriculture, and technology are now the dominant forces reshaping the planet's surface, chemistry, and climate. The parallel is both illuminating and sobering. We are, without question, driving a planetary-scale revolution of our own. We move more soil and rock than all the world's rivers combined. We fix more atmospheric nitrogen than all natural terrestrial processes. And most critically, we are releasing buried carbon from that ancient forest legacy, at a rate that dwarfs even the most intense volcanic episodes of the deep past. The Devonian transformation unfolded across 50 million years. Our climatic impact is compressed into barely 2 centuries. This is the defining difference, a matter of staggering speed. The trees altered the world through the slow, patient pressure of evolution and growth. Our revolution is propelled by the rapid-fire engine of industry and consumption, a geological force operating at digital age velocity. This acceleration strips away the buffer of time, the natural period for ecosystems and feedback loops to adjust. The ancient forests triggered oceanic changes over millennia, giving some marine life a chance to adapt or migrate. Our impact on ocean acidity and temperature is happening so quickly it risks outpacing the adaptive capacity of entire ecosystems. So the open question hanging over this new epoch is not whether we are a geological force. That is already evident in the altered strata of lakes and seabeds where plastic particles and radioactive isotopes will forever mark our presence. The real question is one of consciousness and direction. The Devonian trees were brilliant but unconscious engineers, following evolutionary programming without foresight or choice. We possess the unique burden of awareness. We can read the story written in the ancient rocks and see the trajectory of our own actions in real-time data. This knowledge grants us a potential the first forests never had, the ability to consciously steer the revolution we have ignited. Will we use our intelligence to guide this immense power toward a stable, sustainable equilibrium, perhaps even leveraging natural processes as the ancient forests did, but with purposeful design? Or will we remain passive within the storm of our own making, becoming the first geological force to be overwhelmed by the destabilizing climate it unleashed? The narrative of the deep past offers no guarantees, only a stark precedent that planetary changes, once set in motion, create their own enduring and often unpredictable logic. Our chapter is still being written, and for the first time in Earth's long history, the author is aware of the pen. The saga of Earth's first forests is a testament to the incredible power of life to reshape its own planet. From a stifling hothouse, these pioneering trees engineered a cooler, oxygen-rich world, triggered ice ages and extinctions, and laid the literal groundwork for our existence. Their story, deciphered from fossils and isotopes, is more than ancient history. It is a crucial lesson in Earth system science, illustrating the profound, interconnected, and sometimes unintended consequences of life's innovations. As we face our own climate crossroads, understanding this deep time revolution reminds us of the scale of planetary change and the enduring legacy we are now creating. If you found this journey into our planet's mysterious past fascinating, subscribe for more deep dives into history's greatest puzzles, and let us know in the comments what other ancient mysteries should we explore next.